Okay, let's start our last section. So our first speaker is Professor E.P. Huang from National Taiwan University. This expert in quantum mechanics and information. They will talk about in an organization in quantum mechanics based on the viewers to discuss. Thank you.
Hi everyone. So first, thanks Bo Yao for hosting my section, and also thanks the organizers for inviting me and give me the opportunity to share what we have learned in the past years. First, I think I need to express my appreciation for the everybody who participate, because in this very cross-disciplinary workshop, I actually learned a lot of new stuff, including high energy physics, quantum matter, quantum information, and also AI and stuff. And most exciting part is actually there's a very deep connection between the math and the physics community. So, okay, so. The next thing is I want to mention is about the nature of this talk. So this talk is basically some kind of I'll define it as some kind of interface between the physics community and the mathematical community. So I can provide very detailed algebra, but I will try to avoid that and try to express the physics picture, and hopefully I can define the theoretical concept more intuitively, such that for people with different background can absorb like why we want to work on this problem and what this problem, or how this problem interface the different community. Okay, so the concept that I'm going to talk about today is going to be the concept called interference cage, the quantum many-body scars. So I'll mention later. I'll mention what is quantum many-body scar, what are the quantum many-body scars, and what do we mean by interference caging. But here's like a very brief outline that I hope that people can take away after this talk. So the first thing is that the problem that we are dealing with is more related to quantum ergodicity breaking. So basically, it's a important question in the correlated quantum dynamics community. And what we are doing here is actually we try to bridge this quantum ergodicity breaking problem to the flat band physics, which is intuition, or like the community in quantum matter is supposed to be very familiar with, including like recent boosts of Moiré pattern and flat band high TC stuff. And the cool part that we try to fuse further is that this flat band physics is actually related to some of the math problems that, as a physicist, I have very, very few, or almost like no understanding about. It's called the graph automorphism. And I hope that I can convince you that in the math community, this might also be a very interesting problem. And of course, from the physics background, I'm interested in correlated quantum dynamics in general. Okay, so here is the, by the way, Daolin Tan, who is in the audience, is the primary driving force behind this work. So if you have any question and details you want to discuss, he's supposed to be here. And yeah. And so here's the bottom line or the main message I hope that I can deliver. The first thing is that for a quantum many-body system, we use a Hamiltonian to describe its dynamics, and we use the Hilbert space to, to capture what kind of configuration for a quantum system could be. So the most important ingredient will be like what's the basis and what's the corresponding Hamiltonian. And actually, these two information can be nicely encoded in a graph, but that's not a typical way that physicists think about. But if you think from the exact organization point of view, you will immediately understand why. Because the diagonal term is just like the self-loop on a graph, and the off-diagonal terms in your many-body Hamiltonians will actually be the link between different nodes. So with this kind of complex network, it actually encodes the essential information to give you a well-defined quantum many-body system. Okay. So what I show here are eigenstates for a particular Hamiltonian, and this particular Hamiltonian is basically described by this graph. But the eigenstate A is pretty much very random, And eigenstate B is somehow more regular. And eigenstate C is very strange. Most of the vertex have 0 weights, but only a few vertex has non-zero weights. And its pattern seems to be have some special structure. Okay, so this is the what we call the thermal state, and I will give you a more precise definition about the what we mean by thermal state later. But this is like you have a very random or interacting many-body system, and your eigenstate you expect that the weight will be distributed on various different component or computation basis. But there are several kind of strange eigenstates that actually have very special pattern. And for this, what we call topological ICQ-MBS, which I will more emphasize on, we can see that the structure can actually be understood by interference. So basically what happened is that you assign the weight to be equal weight, equal amplitude, but the sign of the weights will be positive and negative. So after you apply your Hamiltonian on top of that, this weight will be transferred to the intermediate nodes, and they will cancel each other. And since the weight is moved away, so you immediately know that this eigenstate has a 0 energy. Okay, so if you are from the condensed matter background, you'll immediately notice that this is the flat band physics revival, but now not in the real space, but in the many-body Fock space configuration. Okay, so let me try to move forward. So, like trying to create a theory is like having babies. So I actually have 2 babies in the past few years. So I kind of have a very strong resonance about what's going on there. So, they have their own will and they have their own, they want to have their own life. So in this case, ICQ-MBS is similar like that. We try to create our little baby and we hope that it can, survive and sustain for a while. And the other little baby is the density matrix for the T equal to 0 Kitov spin liquid. But since I don't have much time to cover this part, but I want to emphasize that in the poster section, there's another little baby there. And also there's an interesting thing about the duality that, every baby has its own shadow. So sometimes you can try to interface these different things. For example, the interference cage quantum many-body scar also have an interesting connection with the duality, but you just need to, transfer the language from the Fock space to real space again and try to start from the bound algebra type of construction. But if you are interested in that, I'll say more later offline. So this is the outline for today's talk. First, I want to introduce what is quantum many-body scar and why quantum many-body scars are important, or at least for physicists like me, I would like to understand it more. And the second thing is that I want to make this analogy more complete, what we mean by interference caged states. And for flat band physics, it's like a single particle topological localization in real space. But when we promote that into ICQ-MBS, it's actually a many-body version of the topological localization in the Fock space. And the feature of that actually is that it has something called order by disorder that emerge in the Hilbert space, but it's kind of a concept that is relatively, broad applicable. So I would need to use some specific example to demonstrate what do I mean by that. So here, the example that I'm going to use is a 2D quantum link model. It is not limited to that. Actually, you can identify this kind of physics in 1D system also, but 1D is more constrained. So the reason that we pick 2D quantum link model is because first, it's 2D. Dynamics is relatively difficult. And second, it is a gauge theory in disguise, actually. So it's like express that this structure can be expanded beyond the conventional 1D spin model. It actually can be explored in some constrained system. Okay, so why do we care about quantum many-body scar? So when we try to realize some kind of quantum computer or something, the first thing, or at least for me, the first question that I want to ask is how to stabilize it, because it is obvious that it is very difficult to stabilize quantum spins. Okay, but when I try to look up the literature, and what I found is that we've spent a lot of time to, try to fight the coherence of this type, external type. Basically, what do? We try to use a qual state, try to put out qubits in the high vacuum, And hopefully we can shelter these qubits away from the EM field, etc., so that it will not decohere easily. So basically the strategy is you just decouple your qubits with the external environment. But we also know in order to get quantum advantage, we need to couple these little qubits. Otherwise, it's just two-level system, nothing advantage. There's no advantage to take care of it. So you need to couple a lot of them. And if you need to couple a lot of them, it means that you need to make these qubits interact. And that is a problem because once the qubits start to interact, the Hilbert space basically grows exponentially. And once the Hilbert space grows exponentially, then it provides a reasonable reservoir for its own subsystem. So the question is, okay, so if you have only 2 or 3 spins, then you don't need to worry about the fact that the subsystem can actually be thermalized by itself. But if you have 10 or like 200 qubits, the rest of the 100 qubits might become a thermal bath for the target qubits that you want to, operate on. So the question is, if that happened, then it will be a problem because no matter how hard you shelter your qubits, the internal system will basically thermalize this thing. So that's why for us, it will be interesting to understand how to avoid this kind of thermalization. So this is like a very simple analogy of what do we mean by thermalization. So if you have a quantum system and you just let it evolve with time, basically the information will be scrambled and redistributed in your full Hilbert space. It's just like you pour some milk in a cup of hot coffee in the morning and you wait long enough, it will reach some steady state. And if that's the situation, locally, you just do some measurement, you are not able to recover what's going on at the initial time because you only have local information. So even, even if you have different kind of initial condition, what thermalization in the conventional sense tell us is that, after long enough time, you will reach some kind of equilibrium state. Independent of how you prepare your initial state, you will eventually be a well-defined latte. But the problem is that once you enter this latte phase, you cannot extract full information from local observable. So that's what we consider as thermalization. So even under the unitary evolution, that no information is lost, but it's just redistributed in your big Hilbert space. Then local measurement will, stop you from getting the initial full information of your initial state. And there's something that's cut off. I'm not sure how to get it off, but the point here I want to emphasize is that when you enter this kind of latte phase, what is important is that most of the eigenstate basically are featureless. Like you want it to be featureless, otherwise it is not going to look like a scrambled stuff. So that's why we anticipate or intuitively think about the eigenstate for this interacting system should be relatively random. Okay, so here's a very quick review. What do we mean by statistical mechanics for a quantum system? So most of the time we just consider we have a quantum system omega, and we consider there's an external bath B with a well-defined temperature, and we write down the corresponding density matrix for that thing. So that's like the typical textbook equilibration definition for a quantum system. But if you have an isolated quantum system or a closed quantum system, you don't have a well-defined bath because that's the setup we want in the quantum computer. We try to shelter it from the external environment, and we ask how time evolves and will it reach some kind of local thermal equilibration state if we are talking about thermalization. So the first thing is that if you prepare your system in some kind of psi omega state and you just evolve it, and what's going to happen is that that if your Hamiltonian is unitary without losing any information, energy will be conserved and it will be a function of your initial state. Then the question is, how do we define equilibrium if you don't have an external path? Okay, so you can always formally write down something like that, assuming that you have some density matrix, but with some undefined temperature T. So if this line can pass, then you get some kind of formal definition of your temperature T. But it is not guaranteed that this line can always be done. So the important notion here is that can we, like we just described, if you have a big system, if the rest of the system can be a thermal bath of your arbitrary subsystem, then that would be like you try to ask whether it will be a thermal system or not. So we want to, the real target that we are trying to analyze is actually an arbitrary subsystem for that big system omega. So what we are trying to analyze is actually asking what's the long-time behavior for a local system if you trace out the rest of the environment of your big system. And then you ask, after you do this trace, will you get some kind of reduced density matrix such that its temperature is consistently, internally consistently with your previous definition of T. If it is internally consistently, then you have an internal consistency theory saying that this is the definition of local thermalization. And so basically this bunch of mathematics is saying that, or asking the question, will thermalization happen for its arbitrary subsystem at the long time scale? And the second important information is that this temperature, this T, is actually defined by the initial energy of the full system. Okay, so let's move on. So we kind of know, like at least by this hand waving argument, we have a rough picture about what we mean by thermalization. So what we are trying to after is actually not try to thermalize it, because most of the time you will thermalize it. So what we are after is try to avoid thermalization. So it must be not some kind of, it cannot be a generic situation, because if it is generic, easy to avoid thermalization, we probably will see, quantum effect in most of our daily life. But in fact, we don't see that. So the special part that you can try to make this thing a little bit different is that you try to ask like what kind of structure you can impose on your Hamiltonian or Hilbert space. So on a Hamiltonian, the most important structure that we want is locality in real space, because that's how we operate our physical systems. But that does not imply that you cannot have non-trivial structure in the Hilbert space. So that's basically the thing that we are trying to explore. So what kind of non-ergodicity that we can imagine using daily life example is like you have a hot cup of coffee and you try to pour the milk. And if you pour the milk in the right angle with the right speed, you realize that the milk does not scramble itself and you did not get a latte. Instead, you got a phase separation of your milk and coffee. That's like a very strange memory effect. And in classical system, it could happen because of the nonlinear effect. But in quantum system, it is relatively non-trivial because the Schrodinger equation itself is a linear equation. Okay, so how does it happen? Of course, we need to rule out some important ingredients that we know that could lead to this limitation. First is that conventional symmetry, of course, gives you some constraint because Hilbert space will be block diagonalized, etc. So basically, we are asking this question: can we avoid thermalization, but under the condition that we are not using the conventional symmetry to constrain the dynamics? Okay, so here is the pictorial understanding of what do I mean by that. So if you have a many-body Hilbert space, basically the matrix will be an exponentially large matrix. So if you consider the symmetry, you know that you will have some block diagonalized structure labeled by your representations. And the so-called unconventional symmetries these days is that people found that in addition to the conventional symmetry, you can have finer block diagonalized structure within your irreducible representation. And what we are proposing is that this kind of unconventional symmetry is very general, but instead we are trying to point out that there's a generic interference effect that can give you these finer blocks. And that's basically the message that we want to deliver. Okay, so here's why these problems start to get noticed, because high energy physics, condensed matter physics, of course, care about this kind of dynamical problem simultaneously, but experimentally, the driving force is probably from the atomic physics community, because they are able to prepare spatial or temporal manageable systems such that the dynamics can be predicted and measured. Okay, so I probably will not have much time to talk about the details, but here's a very quick survey about what we mean by ergodicity breaking. So for strong ergodicity breaking, what people consider is like the integrable system. Okay, so if you have a many-body system and you can exactly solve it, then of course it is very special. It is not going to be considered as the generic system. And for the integrable system, because you have extensively many conserved quantities, so your dynamics is highly constrained. Okay, so this is not the situation that we are talking about. And the second one is the many-body localization, which involves strong disorder in the Hamiltonian. And what it is doing is because the strong disorder basically create a very complicated energy landscape such that suppress the quantum tunneling effect, and the interference will be, have some statistical contribution such that the particle cannot propagate in the real space. But the point is that it requires strong disorder. So another way to connect to integrable system is that because disorder is so strong that the coupling locally becomes almost like very inefficient, such that you have emergent local conserved quantities. So you will have extensive many conserved quantity, just like an integrable system. So what we are talking about today is going to be quantum many-body scar, which is considered as a weak ergodicity breaking in the sense that most of the eigenstates are thermal, but only few of them violate this thermal intuition. And it is special because of the following reason. First, it's experimentally observed. It's not just hand-waving theoretical tool. And the second is that in certain cases, it can be theoretically exact. You don't need to rely on the disorder. And the third thing is that it actually provides probably the simplest non-trivial mechanism that how a thermal state decouple with this kind of non-thermal state without the symmetry condition. And also, it kind of challenges our understanding this protection is not protected by gap. Because in the community of quantum many-body physics, we know that topological phase is a very robust structure, but essentially it is a ground state physics that's protected by gap. But this physics is basically live in the middle of the spectrum, so the energy gap is essentially exponentially small. Okay, so here's a very quick review about the experiments. So in the experiment, what they did is that they just align a one-dimensional Hilbert atoms. And for Hilbert atoms, they have a very special property called Hilbert blockade. So basically what happened is that the atom can be at its ground state or its Hilbert state, the excited state. Once it is entering the excited state, you will have a process like a very strong dipole moment. And because of that, if two neighboring atoms are both in the Hilbert state, you will have very strong dipole-dipole interaction. So that would be energetically, forbidden. So it creates a very special Hilbert space structure that basically have the constraint that no two Hilbert atoms can be excited next to each other. So the effective model for this system turns out to be this PXP model, and P is just a projector to the ground state, and X is just like the ground state to excited state transition. And this is like a model, but experimentally what they found interesting is that when they try to align these one-dimensional Hilbert atoms to 51 atoms, naively we will anticipate that the system is complicated enough because 51 qubits is like have a huge Hilbert space. But as they try to prepare their initial state in some kind of charge density wave initial state and let it evolve, it turns out that there's a very regular dynamics that we don't anticipate at the very beginning. Because if it is very complicated, what we anticipate should be like, some kind of overdamped behavior. It reaches steady state very quickly. But in fact, it doesn't. So people try to understand what's going on, and it turns out that the initial state, if you prepare it in some charge density wave state, it has a significant overlap with certain type of eigenstate. And it turns out that this certain type of eigenstate have a very special property that its entanglement entropy is actually of area law instead of volume law. And these eigenstates even survive its area law behavior in the middle of the spectrum. And that's very bizarre. The reason for that is if you have a state like that, that means like it immediately violates the eigenstate thermalization hypothesis. The reason is that when you do the subsystem density matrix calculation, you basically trace out the environment. And if it is area law, then what you are getting is that the entropy actually has an area law behavior. But we know that thermal entropy is of volume law, so it's a direct violation. Okay, so that's like where people start to get interested about this business. And of course, people try to describe and understand that through various different theoretical tools. So the two primary approaches, that one is the projector embedding invented by Shiashi and Mori a long time, actually I think even before these experiments. So the idea is that basically using the projector structure, you can eliminate certain kind of coupling between the thermal subspace and the target space that you want to deal with. So that's like a, fine-tuned model, but this mechanism is relatively general. And the second approach is so-called spectrum generating algebra. And this approach basically starts with a higher enlarged symmetry and try to gradually destroy this symmetry to the level that you break all the exact softness property, but you can still keep the a family of special eigenstates as of area law type. So the problem of that is actually these two are mostly rely on the algebra, and is relatively limited because of the fact that it's difficult to generalize to higher dimensional system. And what people found recently is that in the 2D lattice gauge theory by the Bajic and Arnab-Sen, they found that this kind of quantum many-body scar cannot naturally suit into these two frameworks. So the question is, what is the mechanism behind? So here are several principles that we want to tackle this problem. Can we understand that from first principle, like a violation of thermalization? And can we have a generic physical mechanism beyond this algebraic construction? And also we want to understand the question on a different perspective. Previous approach is more like a Hamiltonian with certain properties give us quantum many-body scar. But what we want to ask is, like, for a given Hamiltonian, can we identify certain states beyond the brute force exact diagonalization, and we know that it has the quantum many-body scar or like the non-ergodic dynamics. Okay, so here's like more the scope of the project, because for non-ergodic dynamics, we are kind of define the problem in a negative point of view. And instead of defining problem from a negative point of view, we want to ask more like a positive definition. Under what definition it should be considered like a type of ergodicity breaking physics. Okay, so here is the flat band physics in a very quick review. So here's the time-binding model of a Kagome lattice. Basically, the particles can hop from one vertex to the other. And if you do the solid-state textbook calculation, you'll notice that there's a very special energy spectrum at -2. Okay, you just do Fourier transform, and because there's no translation symmetry breaking, so you can decouple these hopping terms easily. So here I'm trying to provide an intuition like why there's a -2 eigenstate. So I'm claiming that if you put equal amplitudes, weights on this vertex, but with opposite signs, and all the rest of the vertex, if you assign 0 weights on top of that, this is going to be the exact eigenstate with this -2 energy. The fact why it is so, because if you try to apply the time-binding model, this weight will be transferred. And you'll notice that one positive and one negative will cancel here. And you'll see that the weight on the original vertex will be doubled, and its sign will be flipped. And that's where this -2 eigenvalue came from. And it will be exactly the same as the weight distribution that you assigned at the very beginning. Yep.
You have a huge degeneracy in one state.
Yep. So you have one localized state here. You can have one localized state here. You can have one localized state here. So every little hexagon plaquette will give you one eigenstate. But they are not linearly independent, but they are eigenstate. Yeah. The linear independence is not super important for me, but there's some non-trivial topology hidden behind, because how these little plaquettes connect with each other is actually tell you that, the space nature. Can you pad two-dimensional space on a torus? That's that type of question, but yeah. But anyway, the point is that what you need is actually what you got is a real space localization from single particle cage. And this localization has no disorder required. It's not the same as Anderson localization. And because we only rely on the information within this white circle. So yeah, this state is actually super robust. If you add perturbations somewhere here, this state will always be eigenstate. You can add interaction, you can add more bonds, add disorder, etc. And it can also coexist with the itinerant fermion, and this physics is discovered by Sutherland a long time ago. So what we are doing is that, as I mentioned, if I promote that into the many-body basis, every vertex is considered as a many-body computation basis. And the diagonal term is just self-loop. Of diagonal term is just the connection between different states. Then the problem is mapped to a graph. But the only difference is that you lose the translation invariance. So you cannot, do a brute force, simplification for that. So I think, I'm almost like out of time. So, but the point is that this is the type of physics that you anticipate. You got a very complicated graph, and you can identify this kind of caged eigenstates. So since I'm running out of time, but I think I already delivered the most important information. So maybe I'll just leave it in this logical graph. So single particle cage, something that we are familiar with, just do Fourier transform. Many body cage, we are dealing with a complex network, but the same physics can be carried over. The difference is that for many body dynamics, the graph is exponentially large. For single particle physics, the graph is basically proportional with your system size. And the local interference pattern is driven by the same mechanism, but for the graph, for real space localization, the space group and line graph is basically very well mature. But for us, what we are looking for is some kind of cancellation mechanism that require you to have some kind of symmetry property of your graph. That's how it connects to graph automorphism. But this connection, I need to say that it is partially done. Because in order to go from graph automorphism and to identify the corresponding cages, it is actually not an easy task. We have some algorithm to perform that, but the full analysis for this part is still a very highly non-trivial combinatorics problem. And later part I haven't talked about, if you have this cage state, can you directly prove that it violates the ETH hypothesis? We do have this kind of calculation, but it's just more algebra, and yeah, if you want to know detail, I'll say more. Thanks.
For the integrable model,
Yes.
I could graph they have this kind of cage structures.
That's a good question. We didn't really look for that. But the problem is that, let me get back to this. Let me get back to this picture. So for integrable model, the problem is probably going to be like you have many these brown blocks. And these brown blocks for integrable model might be relatively small. So we cannot get into a detail of like how these little blocks, and they have additional interference structure and that. But my suspicion is that there's nothing really stop you from having the similar figures there. But the condition for making it a big story might be a bit more difficult because integrable model itself is already violating the probability physics. So the contrast is not so strong. But so for the ICQ-MDS, the contrast is very strong because most of the stuff is thermal. So only some of them have this kind of problem.
Second question.
Yeah.
What do you mean by backend?
Flat band is just this band is super flat. It's like literally flat. Like you have like the hexagon one band state I mentioned and the n is -2, right? You can do superposition of this -2 stuff with the exponential IKR, and you'll notice that all the energy are the same. So as the function of k, every k has the same energy. So that would be a flat energy band. Yes.
Thank you very much. I was wondering if the EPA's localization system very away from. So we start with a system very far away from the computer.
Yes.
We expect that people community will serve. However, I think that you discuss that you can have like super bits one in the overall evolution. Evolution in which you reach several flash memory state.
Yeah, thanks for that question. I think that's a very interesting question, but I think the first thing I need to distinct is that the steady state and a fixed point in the RT set is different.
Yeah, it's not really a fixed one, it's just like a quasi-stationary state.
Yeah, that would be more like dynamical steady state type of statement instead of using some constraint. What I think is still interesting and not yet well understood is how to do the temporal direction RT. But that is not easy because you basically lose all the nice structure you want to have. So I would say it is something I would like to know, but I have no idea how to tackle it. And I think it is really from the ETH point of view, it's like people postulate that there's a fixed point like that. But even for the proof for many other systems to have localization, there's no proof. It's just a physical argument that I provide. So ETH is still a hypothesis for this H. So